Hey everybody, Trey here. Welcome back to another video. Today we have a very special video for you. Just over a month ago we had the April 2nd, 2025 high-risk tornado outbreak, and a lot of you out there have been asking questions about that forecast. Why was it a high risk? Obviously it verified very well. What went into that forecast? Well, we have the man behind the forecast with us here today. SPC meteorologist Chris Broyles, kind enough to join us today. Chris, how are you?
Oh, thank you so much. Thank you for having me on. We're going to take a look at the April 2nd, 2025 tornado outbreak and what went into the forecast. Thank you.
So, obviously Chris put out the day one initial high-risk forecast. I know it caught a lot of people off guard. So in this video, we're going to go through the meteorology of that day, go through some of the in-house tools that Chris looked at the SPC to actually come up with the high-risk forecast. And we'll show going up from several days before the event to the night before the event when he was actually making the forecast, and going through all those tools to show what went into such, what ended up being such a good forecast. So let's go ahead and get started.
Well, first of all, Trey, I want to thank you for giving me the opportunity to do this interview and to look at this case, April 2nd, 2025. This tornado outbreak was not synoptically evident, but it's a great case to look back on. We got many questions from those on social media, how the high risk was made. And we used tools that have been developed over the last few years. And without those tools, the high risk really wouldn't have been possible. Those tools gave us the confidence we needed to issue the high risk. Before we look at the April 2nd, 2025 tornado outbreak, I want to talk a little bit about the Omega project. The Omega project began in October of 2022. I was at the Severe Local Storms Conference, and after the session was over, I didn't have anybody to go to for dinner, and I walked into the hotel lobby and looked, and there was a young man sitting on the couch, and I said, "You want to go to dinner?" So he said yes, and so we walked to the dinner and sat down, and I'm like, "Well, who are you?" I'm Eric Loken. And so what's interesting about that is that he had developed the Loken tornado probability tool, and I had developed the significant event tornado probability tool. And so we had done very similar work. And so after about an hour, we were like, wouldn't it be cool to see if we can put our tools together and develop something that is really good at forecasting tornadoes and tornado outbreaks. And then that was the beginning of the Omega project. Evan Bentley joined the team shortly after me and Eric decided to get this team going. I had talked to Evan about the 500 jet translation speed. He later came to me and said that he was very interested in helping me to develop the database for that. And from there, Evan told me that would it be cool if we do a web page? And I told Evan, okay, well, I'll get a contingency table together, give it to you, and then you can develop the web page, and then we can have a high risk probability generated from the web page. And so that was one of the tools that we developed early on. Andy Dean was in the process of putting together the 24-hour step. To take the 3-hour step, the significant event tornado probability, and then convert that to a 24-hour. And then from there, Andy and I teamed up to develop the Omega tornado probability. Omega is also a 24-hour tool, and Andy said, well, I'll do the automated code. And I told Andy, I said, well, I'll try to take the 24-hour step and do a manual version, and then after that we can work on an automated version from that manual version. So the way Omega tornado probability is right now is there are two versions, a manual version and an automated version. And so Andy Dean has just finished the 2025 version of the Omega tornado probability. That's very exciting. Jacob Vansel came in to the team shortly after Andy because he was developing verification maps that could be useful to help us with machine learning techniques. We wanted to improve the omega tornado probability, but we also want to develop new machine learning guidance. And we thought Jacob would be really good to help us verify our tools. And I've been working with Jacob recently to develop maps of not only omega tornado probability, but other tornado tools to help forecasters to see how these do in a spatial sense. From the National Severe Storms Laboratory, we have Eric Loken. He's helping me co-lead the project, and his primary responsibility has been to maintain the Loken tornado probability and to help with project direction. He's been a key advisor to the Omega project. Harold Brooks has been looking at verification of high-risk issuances compared to moderate-risk issuances, and has helped us make some key decisions on how to look at the statistical data. Wayne Zhao is a computer programmer from MSCI, and he's going to be trying to develop new machine learning guidance over the next couple of years that will give us an additional tool for us to use on high-risk issuance. From the National Center for Atmospheric Research, David Gagne is a machine learning programmer, and he's been focusing on 500 jet translation speed. He has a software called Haggis-Lag, and we've been trying to modify that software so that we can have automated 500 millibar jet translation speeds for the forecasters, so they won't have to necessarily compute it themselves. Mateusz Tazarak is from Adam Mickiewicz University, and he is developing a 17-year database from the Era 5 that we can train our tools on. This database has the years 2008, 11, and 24, which all had high-end tornado outbreaks, quite a few number of them. But the data set will be used to calibrate the new machine learning guidance at the very high end of the scale, so that we can get more skill for differentiating high and moderate risk. And then Grace Cohen from the University of California, Davis has just joined the team, and she is automating the 500 millibar jet translation technique. We've already made significant progress, and it's very promising. This is one of the harder things that one of the more difficult challenges that we've had, and she's just about got it. She's got the first version ready, and then also she's looking at developing parameters to help reduce false alarm for tornado outbreaks, so that we don't have these cases where we go high risk and then it doesn't verify. I mean, we're never going to be perfect, but the more parameters that we can have that have skill, the better. And she's already making progress in that. If you want more information on the Omega project paper, you can go to the following link. If you have any questions, you can always email me or anybody on the project. So the first I want to go through are the 4 tools that we have developed from the Omega on the Omega project. We use risk impact value to verify these tools. So risk impact value is a number that estimates the magnitude of a tornado outbreak, so that we can be consistent when we look at one tornado outbreak and compare it to another. A risk impact value of greater than or equal to 4 is used to suggest that a tornado outbreak is high risk worthy. Now, on a lot of these events, there's uncertainty. So even if an outbreak can get an RIV greater than 4, there may be too much uncertainty to issue a high. But in a perfect world, if we knew in advance what was the outcome of each of these events, an event with RIV greater than 4 would be high risk worthy. And so what we've done with these 4 tools is we've calculated a POD, probability of detection, of FAR, which is false alarm rate, and over on the very far right, you can see the number of RIV greater than or equal to 4 events, the number of high-risk worthy events that has been sampled for each tool. And then we have a CSI, which is Critical Success Index, and that shows how effective each tool is relative to the other tool. So for instance, the toy outbreak page, tornado outbreak indicator, has a CSI of 0.565. That's the best tool of the 4. And then next on the list is the Omega tornado probability and the STEP and the high risk discriminator. The tornado outbreak indicator is a web page internal to the SPC that we developed that will give us high risk probabilities. And when it forecasts a high, it's right about 2/3 of the time with about a 20% false alarm rate. And that's the best tool that we have this time. There are 212 events that we use to calibrate the toy. Next on the list is the Omega tornado probability, and it generates tornado outlook-like probabilities, contours of 2, 5, 10, 15, and 30. The Omega tornado probability verifies about 3/4 of the time. So 3/4 of the events are caught by this tornado probability, but there's a false alarm rate of about 46%. It's a little bit higher of a false alarm rate. The significant tornado event probability STEP was the only tool on this list that was not created by the Omega project team. I created that in 2005 and then updated it to 2008. In 2008, it is a human learning-based algorithm. It was based on 75 tornado outbreaks, and then the equations were developed using those events, and then it was calibrated on a scale from 0 to 100. That algorithm has a POD of about 53% with a false alarm rate of about 36%. It's been used consistently over the years to contribute to high-risk issuance at the SPC. The high-risk discriminator is a new algorithm that we just developed over the last couple years. It uses STP 700 millibar temperature and 7 to 400 DPVA. It's very effective, actually. With just such a simple equation, we're catching about half of the tornado outbreaks with only a false alarm rate of about 28 to 29%. Now we're going to do a meteorological examination for day 3 before April 2nd, 2025. So this is 3 days before the event. And at my time, I was not working the Outlook desk, but I knew that I was going to be working the Outlook desk for the day 1, the day before April 2nd. So I was going to be doing the 6C day 1. So even out at day 3, I need to examine this event and get ready and think in my mind what I think is going to happen, so that I'm prepared when I get to that 6C day 1 outlook. So the first thing I did 3 days before the event was I took a look at this significant event tornado probability. This is a number between 0 and 100, and when it gets to about 65 and you get this wide color fill, there's a good chance that you're going to get sigtors. And when it gets to 70, that is officially a high-risk forecast. And so I loaded this STEP up and then just kind of went through and noticed that STEP was generating a 70 in far southeast Missouri on April 2nd. In this case, it was a 3Z April 3rd, which should be the evening of April 2nd. This is a 78-hour forecast. This is officially a high-risk forecast because the 70 is a 0 to 100 scale, but when you convert it to the Outlook tornado probability, it converts to a 30. So this is officially a high-risk forecast, and this is one of the strongest signals I've gotten this far out. I don't recall any high-risk forecast beyond 72 hours, so this definitely got my attention and got me ready thinking, wow, maybe we've got a high-risk day coming up on April 2nd, and we're still 3 days away. The next thing that I looked at was the 24-hour STEP. This is a 3-day forecast valid for April 2nd, 2025. What we've done here is we've taken the 3-hour forecast, which you just saw, and then converted it over to a tornado probability. 2, 5, 10, 15, and 30. So this is going to match the Outlook. But this is a accumulation of all the 3-hour forecasts over a 24-hour period. You can see the 30 in far southeast Missouri near the Tennessee state line there. That's a tornado outbreak high forecast. So again, this is just converting that 3-hour data to a format that's more like what we see for our outlook, and just confirm my suspicions. We have a potential for a tornado outbreak day 3. What I wanted to do with the step forecast was to see if it could be potentially a true signal or whether it would potentially be a false alarm. And so the one thing I want to look at to see if there's enough lift for a tornado outbreak. And so this is the 7 to 400 millibar differential positive vorticity advection, DPVA. And within the circle shows the area around that high-risk forecast. You have several bullseyes, one in southern Missouri, another one in far southwest Illinois. And when you go to 3Z, you see that there's still several bullseyes there. Those are showing that there's lift in the vicinity of that high forecast. So I thought there could be enough lift and maybe this signal is legitimate. And the next thing I looked at was the high-risk discriminator parameters. And they're shown here. We have significant tornado parameter, 700 millibar temperature. And what we do is we take the STP, the maximum STP, and then subtract the 700 millibar temperature. And if it's positive, then that is showing potential for a tornado event. And if the STP is high enough and the 700 millibar temperatures are cool enough, then maybe a tornado outbreak. And in this case, we do that equation and we get a positive value. So that was favorable. The tornado outbreak indicator is a web page that's internal to the SPC. So on the day 3 before that event, I did the measurements of the 500 jet translation speed. I got the values from the jet, the maximum speed within the jet and the positions of the jet relative to the forecast tornado outbreak area. And then the STP, the maximum 1 hour STP, entered in the data, and I got a probability of verifying high risk at 57%. This technology is new. It's been developed over the last couple years, but the high risk probability has been calibrated to our database of over 200 events, and it is calibrated well. So when you get a 57% chance, that's going to be pretty good at estimating the probability of high risk. So that gave me confidence that potentially we could have a tornado outbreak on April 2nd.
So could you kind of go through what each of these rows mean, like the east-west distance, total distance from outbreak centroid? I know all of these are talked about in the Omega paper. Can you kind of explain what each of these are and how they correspond to the Omega type calculations?
Yes, good question. So what we did was we noticed that fast-moving jets are often corresponding to tornado outbreak potential. And when you get a 500 jet translation speed over 40 knots, that is generally favorable for high-risk worthy events. In this case, we can see in this 4th row, there's a value of 42 knots that is highlighted there. That is the 500 millibar jet translation speed, and that is determined in an 18-hour window from 6Z, the night before the event, to 0Z, the day of the event. So it's an 18-hour window, and we just get a speed during that 18 hours, total distance divided by 18. And we got 42 knots for April 2nd. This is valid again, day 3. Then also we have the maximum speed within the jet during that 18-hour period. So this is not a translation speed. This is actually a maximum speed in the jet. It was greater than 95 knots. The first 3 rows show where was the jet at 0Z relative to the tornado outbreak forecast area. The tornado outbreak was forecast in the mid-Mississippi Valley. The jet was forecast in southern Wisconsin. So we had an east-west distance, which means you're going directly west-east of the tornado outbreak area expected location to the longitude of the jet at 0Z. So just an east-west distance. Then, if you go directly from the tornado outbreak area to the endpoint of the jet at 0Z, then you measure the distance, and that would be the second row. That's a total distance from the outbreak centroid to the jet. And then the third row here is the direction of the 500 millibar jet at 0Z relative to where the tornado outbreak area is expected. So in this case, it was pretty close to due north, but it was a little bit to the northwest, but it was about 356 degrees if I remember. And so then the final row at the bottom is the STP, and we were expecting an STP of about 9 based on the model data, and we're getting a high risk of 57%. So I'm going to show you some of this in more detail when we go through this again as we look at days that were coming. Now we're going to do a meteorological examination for day 2. Now I came into the SPC again the next day, and I want to get an idea of, are the models more favorable or less favorable for this event coming up? And so the first thing I did again was look at the step. And so this is the 39-hour forecast, and I'm going to just move it out in time here. But by 51-hour forecast, April 2nd at 0Z, April 3rd, which would be the second during the evening, there was a 70 contour. Again, that converts to a 30. When we go to 3Z, we have 2 more 70s over Arkansas. So we're getting 3 70 contours, which again, that would be 30 contour on the tornado probability. So we got 3 of those. So we got a stronger tornado outbreak signal on the step on the day 2. When we looked at the tornado outbreak indicator, the values were identical to the previous day. The measurements were all the same, actually. The models were consistent. So we were getting a very high risk probability of 57%. And so a similar result, but maybe a little bit stronger signal on the step. So the confidence was still there that we could have a tornado outbreak high risk event. Now I'm going to go into more detail about how this was done. Trey, you asked the question, what do all those entries mean on the toy webpage? Well, I'm going to show you what they mean, but we're going to do the analysis first. So we're going to get the 500 millibar jet translation speed. And these are 1-hour forecasts starting April 1st at 1Z. And I'm going to just click through each hour and we can see the mid-level jet. These are 500 millibar isotex and heights. And the jet is in the southwestern U.S. And this is the 6Z starting point of the 500 millibar jet measurement. And so then the jet ejects northeastward into the Missouri Valley and then the upper Mississippi Valley. The endpoint is going to be 0Z. So that 18-hour period is what we're interested in here. And so there's your 6Z starting point right here in the western Texas Panhandle. And then we're going to go to the midpoint, which is 15Z. That is the midpoint. You can see that the jet moved very fast between the start point and the midpoint. And then not so fast during the last 9 hours. The end point was in southern Wisconsin. So we have the start point, the midpoint, and the end point. And so the reason why we do a start, a mid, and an end point is because if the midpoint is too far from either of those, then maybe there's not continuity. And we are looking for continuity. And so you want to see continuity at least at the 3-hour increments. So 6, 9Z, 12Z, and 15Z. If there's too much of a jump between in any one 3-hour period, then it's not going to be an acceptable jet translation. They actually may be looking at two different jets.
So if we go back here to the 6Z starting point, can you give a little bit of insight into how you actually identified the jet that was being used in this scenario?
Yes. Well, what we want to do is identify the central location of the jet. So we do a spatial centroid so that we take the highest contour of the jet, and in this case, the highest contour was 80 knots, which corresponds to this orange color. And then we do a spatial centroid so that you have equal amount of space in the southwest part of the jet as to the northeast. So you put the point right there, spatially centered. And so when we look at the midpoint, you can see we're taking the centroid of the highest contour. And in this case, the highest contour is 110 knots. Same thing at the end point, 110 knots. So now you can see here the start point at 6Z and the end point at 0Z, and the distance was 771 nautical miles. Divide that by 18 and you get your 500 jet translation speed of 43 knots. And in this case, I should say, we're going to use 42 knots as the data entry point because we didn't quite make it to 43. So in this case, we're going to round down to 42 knots. To do the calculation, we're going to need the day 3 outlook so that we can know where the centroid of the forecast was. In this case, the centroid is in far southern Illinois, and so that's where the centroid of the tornado outbreak is expected. We're going to do the east-west distance. So we're going about 40 statute miles to the west of the expected tornado outbreak centroid along the longitude of the 0Z position of the 500 millibar jet. So 41 is going to be the data entry for that measurement.
And so that the position of the 500 millibar jet in this case is that centroid of the jet, correct?
Yes, it's the centroid of the jet at 0Z.
Okay.
And so then we're going to do a direct distance from the centroid of the outbreak to the 500 millibar jet position at 0Z. This is as the bird flies, and that number was 415 statute miles, and the direction was 356 degrees. And so also we need the 500 millibar jet maximum wind speed. At the end point, we had a maximum wind speed of about 150 knots. And we need the maximum 1 hour STP from 18Z to 6Z. So we're looking at that time duration between 18Z and 6Z. Every hour in that time, we're looking for the maximum STP at any 1 hour. In this case, the maximum STP was 9. Here are all the values that we got from the 500 millibar jet analysis. And we're going to enter these all into the web page. We got a very similar result as you saw before. It was the same values that were entered in. So we got a probability of verifying high risk of 57%, just like we did on day 3. So it's very consistent. That's one thing about this technique is that it's generally pretty consistent. And so the models can do a pretty good job of forecasting where the 500 millibar jet's going to be. And so we're not seeing large variances from day to day. And like this is the exact same result that we got from the day before. So it did validate the confidence that we had of a potential tornado outbreak. So now we're going to look at day 1. We're going to do the meteorological examination. Now this time we're going to look at not only those tools, the STEP and the toy outbreak page, we're also going to look at the other Omega tools that are valid for day 1. And then we're going to look at the synoptic data and the model data to get a better idea. Are we having confirming signals, or maybe some of the other things are telling us that maybe this could be a false alarm? So we're going to go back to the parameters that the high-risk discriminator used. SCP, 700 millibar temperature, and we got a result that was very similar. So the models were consistent. This is the NAM, STP, 700 millibar temperature, and we're still getting a value of about +1, when we subtract the 700 millibar temperature from STP. When we look at 500 millibar isotax, the 700 to 400 differential positive vorticity advection, there's still some bullseyes over Arkansas and Tennessee in that area that we were looking at, meaning that it looks like there's going to be lift. And when we look at the NAM discriminator equation, which is the high-risk discriminator, it had a maximum of 11 in Arkansas. What it's doing is it's taking the STP, the 700 temperature, subtracting, and then adding the 7 to 400 dPVA divided by 10. So you come up with a value here of 11 over Northeast Arkansas. And when you take the 0Z value, add it to the 3Z value, like we see here in the upper left, we're getting an added value of over 20. And the threshold for tornado outbreak using this tool is 20. So this is a confirming indicator for the outbreak signal that we're getting from STEP and the TOI webpage. So now this one here is in agreement. It is forecasting high risk. If this value had been less than 20, then it would be saying, no, maybe this isn't a tornado outbreak. Maybe this is moderate risk worthy event. But in this case, it did get to that 20 threshold. So this is officially a high risk forecast. This is not a tool that the Omega project developed. It's a tool that was developed many years ago. And I use it just as another confirming indicator. It was also suggesting tornado outbreak because the number was maxed out at 32. You rarely ever see a 32. It's basically using QPF, SB CAPE, 0 to 6 shear, 0 to 1 helicity, 0 to 2 relative humidity. And it's combining those parameters together. So this was another tool that I had from a while back. And it was also given the potential for tornado outbreak. So I thought, look at it. So we use everything that we can to try to make these forecasts. The model that I trust the most is the ECMWF. We're going to look at the 500 millibar jet and a 3-hour QPF on the ECMWF. And what I wanted to see was, I wanted to answer the question, are there going to be warm sector storms for this event? That was a problem because we had what looked like a boundary that went into the Ozarks. A lot of the models were developing convective potential along that boundary. But was there going to be storms further east in the warm sector? And that was really important on this day. So I was going to look at the ECMWF to see. We're starting out with a 3-hour forecast here. Valid 15Z April 1st, the day before the event. And so the mid-level jet is in the desert southwest, then ejects out into the plains. And then you can see the boundary I was talking about, because what I've got here is I've got CAPE in orange, and then the 500 millibar isotax in light blue, and then the convective precip in the greens, yellows, reds. And you can see there these little splotches along the boundary. That's convective precip. So that's the QPF from the model. And then the lapse rates are the mid-level lapse rates are in the brown and the red hatching out in the western U.S. You can see the lapse rates are real steep. Well, did the ECMWF develop warm sector storms? We can see 21Z, the warm sector and the instability axis is near the Mississippi River, extending up into far western Kentucky. Not many storms at 21Z, but what about 0Z? It looks like the ECMWF does develop convection out in the warm sector along the instability axis. Oh, maybe 100 miles to the east of the boundary. And then that intensifies as we get into the evening on April 2nd. So the ECMWF did have the convective signal across the warm sector. That was enough for me because I know the ECMWF, and it seems to be pretty well calibrated with its QPF signal. And so I trusted it, and I thought that it would have those storms out in the warm sector. And so when we look at the 850 millibar jet from the ECMWF, this is really important because tornado outbreaks have been strongly related to the low-level jet. We've seen that in many studies throughout the years. And in the Mississippi Valley, you want to just see a strong level of jet, and the tornado outbreak will be aligned near it. And so the question is, do we have a low level jet in place for this event? And so with the UCMWF, I'm going to use, I've got the 850 millibar isotex here in blue, the 500 millibar heights in yellow, the vorticity is in the dashed purple, the SB cape is in orange, and then surface dew points are in green. And so when we move this through time, this is April 1st here, and then the night of April 1st. And then what happens during the day on April 2nd? This is 18Z, 21Z, 0Z. If we notice, there are two maximum of the 850 jet, one in Northwest Kentucky and another one in Southwest Tennessee. I was focusing on this little jet in Southwest Tennessee. It's 60 to 65 knots at 850 millibars. That's very strong, low level flow. That is going to be what creates the low level shear you need for tornadoes. The UCMWF had that little jet max there. And I wanted to see, are there other models that also show a low level jet max in that position? And the NAM can do well on the low level jet. And so I wanted to compare the UCMWF to the NAM. There's your 850 millibar jet response that's going to be important for the tornado outbreak on April 2nd. But let's take a look at the NAM. Does it also have an 850 millibar jet centered in the same location? This is during the day on April 2nd. At 0Z, not much there. But then at 3Z, the 850 millibar jet does show up in the same location on the NAM forecast. So you get, it looks like you're getting agreement among the ECMWF and the NAM. When we look at this and compare the two, we can see that they're very much in the same general area. The NAM may be a little bit further southwest, but there is a definite agreement. And if we're going to have the tornado outbreak, we do need to see that 850 millibar jet maximum. That was a confirming indicator. Now we're going to take a look at the surface low. Where was the surface low on April 2nd? Where was it forecast to be? Up in the upper Mississippi Valley by 0Z, April 3rd. That would be the evening of April 2nd. That's pretty far north. And some were asking questions about that. Is the low too far north? So from here, I started looking for analog cases. Do we have a case in the history where we had a tornado outbreak in the lower to mid Mississippi Valley with a surface low that far north? And you can see why the surface low is that far north. Look where the position of the 500 millibar jet is. So far north of the event. Is this a problem? You know, there were many asking the question, well, the 500 millibar jet just brushed the outbreak area. Does it matter that it's so far north? Well, I found a case, March 1st of 1997, using the Violent Tornado webpage. This is the 21Z map from March 1st. The outbreak was in Arkansas. There were 7 EF4s. The mid-level jet was focused in southern Lake Michigan, well north of the outbreak. How about the surface low? Well, on April 2nd, the surface low is forecast to be in the upper Mississippi Valley. What about on March 1st of 1997? The surface low was in Ontario. So it was even further north than April 2nd. And it was not as strong of a surface low. So my question about the surface low was answered with this case. Can you get a tornado outbreak with a surface low that far north? And the answer is yes. And so I was keying in on this event as the analog case for the upcoming April 2nd potential tornado outbreak. So let's take a look at the NAM and look at where was the moist sector? How did the moisture return northward into the lower Mississippi Valley? Were there going to be really high surface dew points? And also importantly, was there going to be low level convergence that you need to get storms in the warm sector? like the ECMWF was showing. This is 0Z the day before on April 2nd. So this would be the evening before 7 o'clock on April 1st. And so we're going to move out in time through the night on April 1st and into the day, April 2nd. This is 15Z, 18Z of April 2nd. You can see what happens here. The surface dew points which are in green, the 68 dew point line, which is here in the lighter color green, is into eastern Arkansas. And then that moves up into southeastern Missouri, where the moist axis is forming and sharpening up. And we got a real enhanced zone of low-level convergence there in the light blues. The light blue kind of, it's like this light contouring in the moist axis area, where you've got these bullseyes of light color blue. That's low-level convergence. And it really intensified early in the evening on April 2nd, according to the forecast, the 27-hour forecast from the NAM. It's a strong area of low-level convergence. And so that provided confidence that, yes, you would get those warm sector storms out ahead of that boundary along the moist and instability axis. And so that gave us confirmation that, yes, our thinking of a possible tornado outbreak here was on the right track. Now, another thing that's strongly related to violent tornadoes is the 700 millibar jet. And so we wanted to look at the NAM to see, is the 700 millibar jet going to be there? So we might get several EF3 plus tornadoes just near or ahead of that 700 millibar jet max. So is the NAM forecasting a jet max to develop? This is 18Z on April 2nd. And then by 21Z, we see this little jet developing in southern Arkansas, which then strengthened over the next few hours until it became a strong 700 millibar jet max, right focused near the Mississippi River, right along the instability in the moist axis, where the tornado outbreak was expected. So this was another confirming indicator. So on this day, so far we have looked at 3 tools. We have looked at the toy web page. We've looked at the high-risk discriminator. We've looked at the STEP. So we've got 3 of the Omega tools showing tornado outbreak likely. And then we have the 700 millibar jet, which is confirming. We have the low-level convergence, the ECMWF that's convecting out in the warm sector. So we're getting a lot of confirmation that our thinking for high-risk day is probably on the right track. So what about the other tornado probability tools? We have several that we look at. Now these are calibrated for tornadoes, but not necessarily tornado outbreaks. And these tools are very useful on your everyday tornado event, and also can be very useful for larger scale events as well. The Jeffs calibrated on this day had a somewhat large 15 across the mid-Mississippi Valley. The STP calibrated also had a large 15. It has 2 close to 15s, one in eastern Missouri, another one that was even larger than the Jeffs calibrated. And then the NATOcast also had a 15 in the same general area, but shifted further southeast. Now, all 3 of these tools, you can see, were pretty close to the same general area, but none of them had the 30 contour. So none of them were forecasting high risk. But again, these tools aren't calibrated for high risk, so that's not necessarily expected. Although they can generate 30 contours, but the Omega tools are calibrated specifically for high risk verification. And this is the 24-hour step from the forecast basically for April 2nd. We had multiple 30 contours that were forecast in the mid-Mississippi Valley. And in a minute, we're going to look at the Omega tornado probability. It's the second best verifying tool for high risk. What it does is it combines the 24-hour step and the Loken tool. Loken is also good at the high end, and it generally does well with 30 contours. So we're going to combine the two. We're going to combine the 24-hour step and Loken to create the omega tornado probability. And what we do is we do even more adjustments to the data so that we can get a better performance result. And so this is the omega tornado probability. This is generated at 4Z the evening before April 2nd. This was the map that was generated, and it did have a tornado outbreak high forecast. 3 different 30s, and the larger 30s placed in the mid-Mississippi Valley, extending eastward into Tennessee and Kentucky. And this ended up being a very good forecast, and it did provide confidence that we are going to have a high-risk worthy event. And so this was the fourth tool that showed high-risk potential for April 2nd. So we had 4 of 4 tools showing that a high risk was the likely outcome. Gave us a lot of confidence. And after looking at all of this data, we coordinated with the offices of Little Rock, Memphis, Paducah, and showed some of these tools, talked about the potential, and all the offices were in agreement. So the high risk was ready to be issued. Next, I want to show you how the Omega tools, specifically the Omega and the STEP, verify compared to some of the other tools that we use. Omega and STEP both have a CFSI of greater than 0.4, while the other 6 tools that we use, the CSI is generally between 0.25, 0.25 to about 0.10. And so these other tools, like I said before, they're not calibrated for 30 contours. And so the Omega tools are, and they perform really well when you look at this metric. But the Loken tool, it doesn't verify as well. But when you combine it with STEP and then you make the adjustments, it does improve Omega. As you can see, Omega has a higher CSI than STEP. And one thing about Loken is that the POD is a little bit higher. The false alarm rate is still acceptable. So it was good to be able to combine STEP and Loken. It made a better result, and so that's why we did that. And Loken is also added to STEP so that for all tornadoes, the probability can be calibrated for other kinds of events, like maybe isolated or regional tornado events. So Loken makes the STEP and the combination of Omega much better at predicting all tornadoes. So what did the STEP show for April 2nd? This would be valid for the 60 day one outlook. So this is what I looked at when I was preparing the 60 day one outlook. It has a 70 in northern Missouri, another 70 in western Illinois, then a large 70 in southeast Missouri, northeast Arkansas, and then another 70 at the very end here at 6Z. That would be April 3rd. So that's 1 a.m. on the night of April 2nd. And so I go back through this, and you can see there's quite a few 70s here. That's definitely a strong tornado outbreak signal. Which of these 70s are the ones that we're interested in? Well, the first thing I know from experience is to find the biggest one. There's the biggest 70 contour. So that's kind of where I'm thinking, okay, this is maybe where the best tornado outbreak potential might be. And another thing I know from experience is to look at where the last 70 is. Where does it consolidate at the very end in western Tennessee? So these 2 times were the ones that I was kind of really focusing on where the tornado outbreak might be. Well, that evening, I'm doing the 60 day one outlook. But before I make the high-risk decision, I've got to do the toy webpage analysis, the 500 millibar jet analysis that I was showing you before that we did on day 2 and day 3. The question was, is it still going to give us a 57% chance of high risk, or is it going to be higher or lower? And so if we go to the 500 millibar jet and get a starting point at 6C, that's 1 a.m. the night before the event. it was in southern New Mexico. One thing I noticed is that it's much further southwest with the starting point. The previous analysis points were in the western Texas Panhandle. Now we're getting southwest into southern New Mexico, which is much further southwest. When you go to the midpoint, it's still in the Kansas City area. The endpoint is still in southern Wisconsin. So the distance is much greater traveled for the 500 millibar jet from 6Z to 0Z. During the 18-hour window, the jet traveled much further on this analysis. There's the start and the mid and the endpoints. So when we look at the STP, the 1 hour STP, the max was around 11. So that's higher than what we had before, which was 9. So now on this analysis, we're getting a greater STP max. So what happens when we enter in the data for the 500 millibar jet analysis in the STP? The high risk probability jumps up to 85%. If you notice, the main difference here is the speed of the jet, which was 42 knots, is now greater than 45 knots. As a matter of fact, it was above 50 knots. And it's because that jet was just ejecting out faster. And when it ejects out fast, that helps. The hypothesis is that helps produce large-scale ascent across a broad area to the east of the jet. And in this case, we needed that large-scale ascent to spread across the tornado outbreak area. And because of the fast movement of the jet and the higher STP and the favorable location of the jet relative to where the tornado outbreak was, especially in a longitudinal sense, the probability of verifying high risk jumped to 85%. So to me, this was the final tool that made it high confidence for a high risk outcome. At this point, I talked to the forecast team. The lead forecaster set up a conference call for me to talk with Little Rock, Paducah, and Memphis. And with these tools, we were able to show that we were confident in high risk issuance, and they were in agreement to go ahead with the high. And so the question then, where should we put the high risk? Omega tornado probability showed the potential for high risk in the Mississippi Valley, extending eastward into the western Tennessee Valley and the lower Ohio Valley. And this seemed like a good forecast. Now, from experience, we know that in April, the model forecasts tend to be pretty good because you're not in the cool season, you're not in the warm season, you're kind of in between the two. You're in the transition period. And historically, the models have shown that the forecasts in April tend to be pretty good. Now, they're not always good, but we trust the models a little bit more in April than, say, we do in the summer when they tend to be too fast, and in the heart of the winter when they tend to be too slow. So that gave us confidence that perhaps the forecast here from Omega tornado probability was pretty good. And then from experience using the step, the maximum contour, the largest contour, I should say, from the step was at the 27-hour forecast 0Z on April 3rd there. So that's 7 p.m. on April 2nd. That's the largest contour that we had. And then the 70 at the very end, which was the consolidation point at the end at 6Z. And that was at night on April 2nd. And so I know from experience with the step that the central rate of the tornado outbreak is probably going to be between those two. And that's where I put the high, was in the Mississippi Valley. This is the high risk that was issued on the 60 day one outlook. It was centered on the Mississippi River, Northeast Arkansas, Western Tennessee, Western Kentucky, and Southeast Missouri. Confidence is substantial that we're going to get the high risk to verify. There wasn't much doubt with this event. we had 4 Omega tools giving us a high risk forecast. And then we had lots of different indicators that we looked at from the models and from other tools as well. The toy risk probability of 85%. It seemed like that this was going to be a high risk event. So the question is where to issue, and I think we were also confident on the placement of the high. One thing I wanted to talk about a little bit before we look at the verification result for this event. With the 500 millibar jet being so far north of the expected tornado event location, was that a negative factor? The question was a good one. I mean, this was very far north of the tornado event. But when we look at the 500 millibar jet and we draw where the right rear quadrant of the jet was, it was a large area. I'm starting here at about 60 knots, and I'm drawing the edge of the right rear quadrant of the jet across the lower Mississippi Valley into the lower Ohio Valley, and then all the way to the higher speed max, the axis of the higher wind speeds. Because the jet moved out so quickly, and then we also had a very large entrance region of the jet across the Ozarks, large-scale ascent was spread over a large area. And that's really important for a tornado outbreak, because if you have an area of very focused large-scale ascent that's very small, then it's going to only be favorable in a small area. And for a tornado outbreak, we need it to be spread out over a large area. And so you can see that the large right rear quadrant of the 500 millibar jet is favorable for a tornado outbreak. When you look at the 4 quadrants of the 500 millibar jet, we see that the left front quad was actually very small. The right front quad was bigger, but the right rear quad was very big, very large on this jet streak. And so that was favorable. And so the high risk was put on the edge of the right rear quadrant. And you can see where it was. It was just right on the far eastern edge. And if you notice, there's an axis of higher wind speeds extending off the jet across the Ozarks in southern Missouri and northern Arkansas. It was co-located with the high risk. And we think that that axis of higher wind speeds was important to the tornado outbreak, and that ascent was concentrated just to the east of that axis. So let's take a look at how the forecast did. The first thing I'll show is the April 2nd tornado outbreak. This is the outcome. These are the tornado tracks that happened on April 2nd. The yellow tornado triangles are F0s, orange F1, red F2, and the blue are EF3. And then in addition to that, I've got the highest DPI, the disaster potential index. The highest 5 tornadoes are ranked 1 through 5, and you can see the location of those. And so the first thing we see is that there was a clustering of 3s, and it looks like longer track 3s because each one of these triangles represents a 10-mile track length. So if a tornado track was 40 miles long, then it would have 5 triangles actually. So if it was just 6 miles long, then it would just have 1. If it's 15 miles long, then it would have 2. So that's how the triangles show the path lengths of these tornadoes. And so we had several long track EF3 tornadoes in the mid-Mississippi Valley. And then if you look at your higher DPI tornadoes, they're also concentrated mostly in the mid-Mississippi Valley. We've got one here that was further north in eastern Illinois, but most of them were clustered around where the high was issued. Now, where was the high issued relative to the tornado plot here? It was pretty well spaced. I think that it could have been bigger and extended further southeast into northern Mississippi and western Tennessee. So It wasn't perfect, but it was good. It was a good forecast from our verification standpoint here. It could have been bigger, and it could have been further southeast. And when we look at RAV, the risk impact value, a number greater than or equal to 4 verifies high. This outbreak it basically had an RAV of 12.5, which is sort of mid-range high risk. So definitely this event was high risk worthy, and it was strongly so. It was definitely a solid high risk event, and the high risk that was put out was co-located fairly closely with the tornado outbreak centroid.
So that's going to wrap up this video. I want to thank Chris for joining me today and going over what went down with the April 2nd forecast. It ended up being an amazing forecast, and so we all commend you for that. So thank you so much for sharing your thoughts on how you made that forecast. Do you have any final thoughts you'd like to add?
Yeah, these forecasts are not done lightly. When we put out a high, it affects multi-state regions. Businesses close, schools close, families plan. Impacts a lot of people, and so it's very difficult to make these calls. But the Omega tools were developed to assist us so that we can make them, we can make the high risks more accurate, and we can get them out earlier in time. And it's really unfortunate this event occurred, but the SPC was put into place to forecast these major tornado outbreaks, and that's what it's all about. It's just trying to get forecast out in time so people can plan and make appropriate actions to protect themselves. So that's the main thing. But I appreciate Trey for allowing me to be on, and thank you very much. Thank you.
Yeah, you bet. Thank you so much for joining us today and going through your thoughts. So that's going to do it for this video, guys. Thank you so much for watching. We'll see you next time. If you're interested in learning how to forecast these events like Broyles, check out the Chaser Academy over at stormchasercoaching.com. Once you subscribe, you'll find monthly, in-depth modules and other content that will level up your forecasting skills and help you chase these setups like the pros. You won't find this quality of content, which is specifically designed to help you become a better forecaster and storm chaser, anywhere on the internet, so subscribe to the Chaser Academy today.